Today's class, we're going to talk about the electric field. And the electrical field is a more abstract quantity than the electrical force or than electrical charge. And so we're going to spend some time learning about this new abstract electrical field and working with problems, questions with this new abstract electrical field. So specifically, today's class, I'm going to introduce the idea and define the electrical field. That's our first thing. I'll talk about calculating the electrical fields of arrangements of electrical charge. We'll talk about sketching electrical fields of arrangement of electrical charge. And then finally, we'll talk about electrical fields in the context of electrical conductors, and some special rules for electrical fields in the context of conductors. So that's today's content. So let's begin by introducing electrical field. Who is he? And the concept of the electrical field and quantitatively defining the electrical field. So I'm going to start here, action at a distance. So action at a distance is a phrase in physics. The electrical force described by Coulomb's law is action at a distance. So Coulomb's law explains the electrical force, but it doesn't say how it works. It just says that two charges at some distance exert forces on one another, but does not say how that force works. Gravitational force, Newton's law of gravitational force. That's also an action at a distance force. So it says how two masses, here and here, interact with one another gravitationally, the forces they exert on one another, but it doesn't describe how that works. So that's actually a very shaky foundation for a fundamental law, like Coulomb's law of electricity, for a fundamental law like Newton's law of gravity, that the laws don't explain how the forces they describe work. Those forces of gravity and of electricity are quite different from everyday forces like friction or tension, normal forces. They're different in the sense that friction, normal force, tension force involve contact, involve objects in contact, involve touch between objects. So there's no need to explain how the force gets from here to there. But for gravity and electricity, we need to understand how the force gets between the two charges, how the force gets between the two masses. And so far in Coulomb's law, Newton's law of gravity, there is no such explanation. Okay. So that's all to build up the entrance of the electrical field. And also we'll talk about gravitational fields. So the electrical field and the concept of fields was introduced by a very famous scientist, made enormous contributions in electricity and magnetism. He's one of my favorites. His name was Michael Faraday. I kind of like him because he had no proper education in science. But he made these enormous contributions to science. And a lot of these contributions were through his intuition and his experiments. So the introduction of the field, the concept of the field, is due to Michael Faraday. And basically, he said that the force, electrical force between two charges, is actually carried or mediated or conveyed between the charges by an unseen, invisible messenger that we call the electric field. Likewise, the force between two masses is carried or conveyed or transmitted between those two masses by an unseen, invisible gravitational field. So that's Faraday's original idea. It's sort of ironic that actually, I said the problem with gravity and electricity was the action at a distance. We said that we could understand tension, friction, because it's contact. But actually, tension, friction, normal forces are action at a distance electrical forces between the individual atoms and the molecules that are making up the materials. Those materials aren't really in contact. There's microscopic separations between those materials. And it's action at a distance electrical forces that are tension, are normal force, are friction force. You know, I'm standing on the ground, but I'm not touching the ground. You're sitting on the chair, but you're not touching the chair. There's a space between you and the chair. There's a space between me and the ground. It's microscopic. It's atomic molecular size space. The normal force of the chair on you, of the ground on me, is being transmitted over that distance by an electrical field. Okay, now we've got to define the electrical field. Quantitatively, precisely define the electrical field. That's this slide here. So this is the definition of the electrical field slide. In this slide are two charges. There's one I just call Q. I call it source charge. There's one I call Q naught. I call it the test charge. Let me explain what those two are. So the source charge is the charge that we're imagining, so the charge distribution we're imagining, that's creating this invisible electrical field. So that's what the source charge is doing. It's just creating an electrical field. The test charge, what's that doing? The test charge is like our probe of the source charge's electrical field. We're going to use that little test charge, Q naught, to probe the strength, the direction of the electrical field. And the way that we do that is that if we know the charge on the test charge, we know its size, we know its sign, and we measure the force on the test charge due to the field that the test charge is immersed in, we can calculate the field from the force and its charge by what we call the field equation. So this equation here is what we call a field equation. It relates the force on the test charge, so that's the F here, and the charge of the test charge, that's the Q here, Q naught here, to the electrical field that conveyed that force. So if you look on the right-hand side of the field equation, those are concrete things, the amount of charge that the test charge has, and the amount of force that the test charge experiences. So those are concrete things we can measure. From those two things, the force it experiences and the charge that it owns, then we can calculate this unseen, invisible electrical field that carried that force by this field equation. And so that's this is really how we explore or how we probe an electrical field with a test charge. So this equation defines the electrical field in terms of an experienced electrical force by a charge, a test charge. And it's called the field equation. Using Coulomb's law from last class, that's the electrical force of a point charge, and using this field equation I've introduced in this class, we can actually write down little formulas, equations for the electrical field of point charges, which again is going to be a fundamental building block of us understanding of electrical fields, of arrangements of charge. And so I've done this on this slide for a positive charge. I've done it on the next slide for a negative charge. Let's look at these two fields. So on this slide, this is to document for us the electrical field that's created by a positive point charge. And so, look, here's the positive point charge, that's the source charge, Q. Here's the test charge, Q0, it's the probe of the electrical field. If I place this test charge at distance r from the source charge, it experiences a force that's given by Coulomb's law. And so I can calculate the field of a test charge using the field equation and substitute in the force that this test charge is experiencing. It's a Coulomb's law force given by this little equation here, Coulomb's law. Divide it by the charge, Q0, of the test charge. So I'm going to divide it by Q0. You see that the Q0's cancel out in the numerator and denominator, and we get this expression here. This is an important expression. It's the expression for the field of a point charge, the field of a positive point charge. This is the size of it. It's K, Coulomb constant, times the amount of charge that that charge owns. So bigger charge creates a bigger field, smaller charge creates a smaller field, divided by the square of the distance from the charge. So the field, like the force, gets weaker as you move away from the charge. You double the distance, you quarter the field. And so this is the equation for the strength of the field of a point charge. In the case of a positive point charge, which is what I'm picturing here, that field points in the same direction as the force. I'm dividing F by a positive number for a positive test charge. And so the field is in the same direction as the force. So in this case, the field is pointing outwards, radially outwards from this positive charge. This is the same slide, but for a negative charge instead of a positive charge. The only thing I changed was I made the positive source charge a negative source charge. The only thing that changes for the test charge is that instead of the test charge being repelled from the positive source charge, now the test charge is being attracted towards the negative source charge. The strength of the field of a negative test charge is the same as the strength as the field of a positive test charge. Same formula. Coulomb constant times the size of the charge divided by the square of the distance. The thing that's different is that the field is directed not away from the test charge. That was the positive, not away from the source charge. That was the positive case. It's directed towards the negative source charge. That's the negative case. So on this slide, just think about the difference between this slide and the last slide. The only real difference is that when you have a negative charge rather than a positive charge, the field lines head towards the negative charge rather than away from the positive charge. The force, therefore, is attractive for the negative charge. The test charge is being pulled inwards rather than repulsive for the positive charge where the test charge was being pushed away. So those are important ideas for the fields of positive and negative test charges. Positive and negative point charges. Okay. Any questions on all that? So I'll move on to an example, an illustration involving the field equation that we've just discussed. So in this particular problem, we're told that we've got a tiny oil drop, 3.8 grams, is charged minus 18 microcoulombs. And it's just floating in this uniform electrical field. So it's at rest, floating, suspended in this uniform electrical field. And from the information given, which is the charge and the mass of the oil droplet, we're going to figure out the electrical field that this charge is floating in. And this is an example of working with the field equation, which is the relationship between forces and the fields that carry those forces. So let's go ahead and do this. I think I'm going to do this on the document camera. Okay, so I did start it ahead of time. I started drawing my sketch, which is my sketch of my sort of mental image of the problem. And that sketch, typically in that sketch, I will put on that sketch the physical quantities that are important for the physics problem. I'll label physics quantities I know or don't know in that physics problem, but I'm also going to add the core ideas, the core concepts in solving that physics problem. And so I've started here. Here's my oil drop in the center. Here's my charge and the mass of the oil drop. I know these, so I've labeled these. And then here's the key concept. This charge is floating, is suspended in midair, like some magic trick. It's floating, it's suspended in midair because there's equilibrium of forces. There's an electrical force and a gravitational force. We've suspended it in a gravitational field that creates we've suspended it in an electrical field that creates an electrical force which is counterbalancing the downwards pull of gravity. And so I've pictured that here. Look, this arrow downwards is the force of gravity. I call it Fg. It's pulling the oil drop towards the floor, and there must be, if it's floating, an electrical force that's pulling the oil drop towards the ceiling with an equal strength but an opposite size. Okay. Now let me start adding some things to this. What's key is I know this pen isn't working. I know this expression for the gravitational force, mg. Actually, you can now think of this as a field equation. G is the gravitational field conveying the force. M is the mass that's experiencing the force. So this too is a field equation. Upstairs here, the relationship between the electrical field and the electrical force is given by this equation here. This is, again, the field equation. So I'm just adding my understanding of the force of gravity, the force of electricity in terms of the underlying fields that convey those forces. So that's a little bit of detail that I've added, a little bit of understanding that I've added. And then I'm going to write over here kind of the master equation for this. My F's are terrible, I'm sorry. That didn't look like an F at all. It looks like some hieroglyphics that prehistorics used. I'm going to try harder on this F. Okay, the core idea is equilibrium. That this gravitational force and this is stupid, and this electrical force, this is an E now, sum up to zero. So that's the key idea. So now let's see if we can, from that key idea, answer the question of what's the what's the electrical field? Now, if I'm going to answer the question of what's the electrical field, I'm going to answer the question of what's the direction of the electrical field and what's the magnitude of the electrical field. So we've got to do both those things. Let's start with direction. So direction. I'm going to start with something I know. Gravity is down. If gravity is down and I've got equilibrium, I know that the electrical force is up. And from the field equation, I know that if the electrical force is up and I've got a negative charge, then the electrical field must be down. For my negative charge to experience an upward electrical force, it must be in a downwards electrical field. Think of the field equation. You've got a vector, the force, you've got a vector, the field. If the charge is negative, then the field and the force are in opposite directions by the field equation. So this last step is because we've got a negative charge Q. If it was a positive charge Q, if the force was upwards, if the electrical force was upwards, then the electrical field must be upwards too. Okay, now we want the size. Okay, so let me take that equation for equilibrium, that the sum of the electrical force and the gravitational force must add up to 0, and rewrite it in terms of the sizes of the electrical force and the size of the gravitational force. So if I'm going to do that, I'm going to rewrite it as the following. Fe now, I got no line over the top to indicate it's a vector. This is just size of the electrical field. Fg, no line over the top. This is just size of the gravitational field. I've got pluses and minus signs for my equilibrium, that these two things come to 0. The plus is saying that the electrical field is up, and therefore the gravitational field is in the opposite direction. The minus sign says it's down. So it's just a rewriting of equilibrium. Now I'm going to fill in how I understand the two forces are related to the two fields. So let me do that. And so that's what I've done here. E and G, that's the electrical field strength, and the gravitational field strength. So their sizes, their magnitudes. M and Q is the mass and the size of the charge. So be careful here that everything, all the symbols, the way I've written it here, are now sizes, magnitudes. The directions I've encoded in the plus sign and the minus sign. I put a little magnitude symbol around Q because that's the one that can become confusing in this problem, because that is physically a negative charge, but this equation here, it just involves the magnitude of that negative charge. There's no confusion about, oh, what about maybe mass is negative? Well, mass isn't negative, so you can't get confused about that. But charge can be positive or negative, so we can get confused about that. Okay, so now we're almost there. This is like a little algebra problem that we like, and we've just got to rearrange it for the unknown, which is the electrical field. And so if I rearrange it, I'm still on the screen. I'm going to get this little guy here, mg over q, and I know everything on the right-hand side. I know the mass is 0.0038 kilograms. I know the acceleration of gravity, 9.8 meters per second squared. I know the charge is, 18 times 10 to the minus 6 coulombs. If I plug all those numbers in, I won't write them all in, it'll be illegible. But I've already calculated the answer. I got about 2,000 69 units of newtons per coulomb for the electrical field. And so that's the solution of a problem that involves the use of our understanding of the relationship between fields and forces, that fields carry forces. We've been able to use that understanding, in this case, to figure out the charge on that oil drop, knowing the electrical field. This is actually a very famous experiment in physics history. So a little over 100 years ago, an American scientist got a Nobel Prize for doing exactly this. I mean, I'm not solving that problem, but suspending tiny droplets of oil, having them float, suspended in air, in a known electrical field. Why would he get the Nobel Prize for that? The reason he got the Nobel Prize for that, when he measured the charges on those droplets, like we just did, he found that the charges came in units of 1.6 times 10 to the minus 19 coulombs. He, for the first time, found that electrons have a certain unit of charge. When you charge something by rubbing, and he was charging these oil drops effectively by rubbing, he could only get 1 unit, 2 units, 3 units, 4 units, whole numbers of electrical charges on the oil drops. And so that was a huge breakthrough, huge discovery from this simple example here. Okay, I got a quiz here. I forgot about that. So, again, this quiz will count for credit. There's 2 points for a correct answer, 1 point for an incorrect answer. I will have to go in after the lecture and give you ones if you've got it incorrect, because it automatically gives you zeros. Let me post it. That would be a good idea. And let's see, it's coming up to 10 o'clock. So you should see it published now, I think. I asked you to think about 2 charges. Q1, Q2. One's a larger size, the other one's a smaller size. And it asks, do they experience the same electrical forces in size? And it asks, do they experience the same fields due to the other charges? So it asks you to compare the size of the forces they're experiencing and the size of the field that they're experiencing due to the other charge. And it's the sizes of the forces and the fields. Don't have to worry about the directions of the forces and the fields. And so I'll give you a couple of minutes to think about that. Yeah, and feel free to chat about it, because chatting about physics is one good way, active way of learning about physics. So chatting is good.
promise I'm not lying. I clicked the wrong one, and I can explain to you why.
Just, do you want to send me an email
Yes.
after class and I'll sort it out?
Thank you.
Yeah. Okay, I'll get started again. So just to give you the answer, these two charges, one is big, one is small in size, they do experience same size forces. So the forces are always equal and opposite. That's Newton's third law. So although one charge is big, one charge is small, the forces are equal and opposite. It's like actually that, you're small compared to the Earth, and the Earth is big compared to you. But the force that you exert on the Earth, gravitationally, is the same size as the force that the Earth exerts on you, gravitationally. So the forces always come in pairs and always the same size. But if you're a big charge, you're going to create a big field. If you're a little charge, you're going to create a little field. So in this problem here, we got a big charge sitting in a little field, but it kind of feels it a lot. And we got a little charge sitting in a big field, but it only just feels it a little bit. And so the fields are different, but the forces are the same size. Is that sensible? Okay. I want to talk about superposition principle. So we talked about superposition principle for electrical forces. Now I'm going to talk about superposition principle for electrical fields. It's going to give us a little deeper understanding of the superposition principle. So the superposition principle for electrical fields is that the net or total electrical field at some point, location in space, we sometimes call it the field point, where we're interested in the field, is the sum, the vector sum, of the electrical fields, individual electrical fields, of all the surrounding charges. So to get the total electrical field, you've just got to add up the individual electrical fields of the surrounding electrical charges, remembering that those electrical fields are vectors. So here's an example of that. I got this point here. So this is now the field point. There doesn't have to be a charge there. There could be a charge there, or there may not be a charge there. We're just thinking about it as a point in space we're calling the field point. What is the electrical field there? It's the sum of the electrical field due to this charge downstairs here in tangerine, and this charge over here, number 2, in olive. So the tangerine and the olive charges create their own individual electrical fields at this point. I pictured them. Here's E1, the electrical field of this charge. It must be positive because it's pointing away. Here's E2. It's the electrical field of this charge. It must be negative because it's pointing towards it. And then here's the sum of those two vectors. This is the net or total electrical field. If you want to see the vector addition, here's an example. So we could picture the vector addition of the two fields by drawing one of the vectors. Here's E1. Here's its tail. Here's its tip. Then I draw the second vector, E2. I put its tail at the first vector's tip. And then the total or net electrical field, that goes from the tail of the first vector to the tip of the second vector. That's how you draw vector addition. And so here's the resulting electrical field. So that's superposition principle. It's exactly the same for electrical fields as it is for electrical forces. You've just got to add up the individual electrical fields, individual electrical forces to get the total electrical field or electrical force. So let's look at examples of this. Here's a very, very famous example, the water molecule. So the water molecule is interesting in part because it's what we call an electric dipole. So the water molecule kind of has two ends to it. There's the H2O molecule has two ends to it. There's kind of the hydrogen end and the oxygen end. And the hydrogen end is more positive. I'm checking I'm remembering this right, because I can never remember. I can't remember left and right. I can't remember plus and minus. There's a disease, a problem, a psychological problem related to that. Anyway, it has a positive end for the hydrogen, has a negative end for the oxygen, and that's what we call an electrical dipole. Electrical dipole is an arrangement of charges that is overall electrically neutral. Water molecules are electrically neutral, but it has positive and negative ends that are separated by some distance. So that feature of water is very important, right? That feature of water is why you get water, why it becomes a liquid and not a gas at, say, room temperature. It's because the attractions of the electrical attractions of these electrical dipoles that are the H2O molecules. And it's also why water is it's important for life and your body and whatever, is a very good solvent. So you put salt in water or sugar in water, it dissolves the salt or the sugar because of this electrical environment that water is. It pulls apart the sodium chloride crystals into separate sodium and chlorine ions. And it's all because of this dipole characteristic of water molecules. So we should be thankful for it. Okay. So here's a more abstract picture of a water molecule or an electric dipole. So here's the positive end, and here's the negative end. And I've placed them on the horizontal axis about the origin. And the positive charge is distance A to the left, and the negative charge is distance A to the right. And we're going to figure out what is the resulting or net or total electrical field due to this arrangement of electrical charges at some point, field point, up here. This is on the midplane. So this axis here is the midplane between the two charges. It's halfway between the two charges, equal distance to the two charges. Anywhere on this line, we're going to find the field here. And the way that we're going to find this field is using the ingredients we've introduced. We're going to use that equation for the field of point charges. And we're going to use this idea as superposition. So we're putting together the building blocks we've sort of constructed over the class so far. Okay, so the way that we're going to do this is we're going to write down the fields of the positive and negative charge, expressions for them. We'll write down the horizontal components and vertical components of those fields. And then we'll add up those horizontal components, those vertical components. That's how we're going to deal with the vector addition of these two electrical fields to get the total resulting electrical field. And we're going to find an interesting result. I think I'm going to try this on the document camera. And so here we are. I started this problem a little bit by making the sketch of the two charges and where they're located. And upstairs here this pen doesn't work. That's the field point. So if you look at the sketch so far, I'm kind of indicating all of the geometry of the problem. Plus q on the left, minus q on the right, distance a in each case from the origin, distance r in each case to the field point. Look, there's an angle here, theta. I'm labeled it because I'm going to use it later on. It's the angle of a right-angled triangle that's formed on the left and right-hand side of that midplane. Because I'm going to use it later on, I'm going to write down that the cosine of this angle, which is, the ratio of the adjacent to the hypotenuse, is in this case a over r. So that's going to be handy later on. Okay, so let me start by adding some understanding. So these two charges will produce two electrical fields at this field point. So I'm trying to draw these. This one upstairs, I'll call this E1. It's just due to the left-hand charge. And this one, E2, due to the right-hand charge. For some very strange... Oh, what's going on here? Somehow I hit brightness. Oh, that's crap. Because I don't know where brightness is. That's what happens in your head when you've been working on a problem too long. Here we are. Okay, so these are the two individual electrical fields. Now, before I go on and do the math of adding them up, I always like to warm up on the ideas of adding them up. There's an interesting thing here, right? That, let me draw another horizontal here. The angle of E1 with respect to that horizontal is theta. The angle of E2 is also theta. They're above and below the horizontal by the same angle. This pen is too thick, so that's useless. So that means that they're vertical components of those two electrical fields. You can see it. You already know what I'm saying here. It's going to cancel out. E1, whatever field it has up, is canceled by E2's field down. So those cancel out. So we don't need much math. We don't need any math, really, to recognize that there is going to be no electrical field up and down when you add these two fields together. The only electrical field that's going to rise is horizontally, because E1 has a component of its field towards the right-hand side, and so does E2. It has a component towards the right-hand side. So when you add up these two fields, you're going to get a resulting electrical field that looks like that. And so all we've got to do is find the size of the that. How big is that? And so that's our real task. So how am I going to do that? Let's just note that the size of the field E1 overall is kq squared over, not kq squared, kq over r squared. And the size of the field E2 is also kq over r squared, because they're just fields of point charges. So that's the strength of those fields. Now, if I want to find the net field, the one I labeled just E, all I need to do, maybe I'll label it ER, is the resultant, is find the x component of field number 1. I'll call that E1x, seems sensible. X component of field number 2, I'll call that E2x. And these components of these two fields are going to be the size of the field, so that's a kq squared. I keep saying q squared, I don't want it, go away. Kq over r squared times, I want this horizontal component of that field, it's cosine theta, which will tell me, or give me the horizontal component. You see, the field is like the hypotenuse of a right-angled triangle. The horizontal component is like the adjacent of that right-angled triangle, adjacent to the angle. And so multiplying the field strength by cosine theta will give to me the component of that field in the horizontal direction. It's actually the same thing down here for E2x. And both of these, I know one is a negative charge, one's a positive charge, one's a field that points towards and one's a field that points away of the charge, but both these components are towards the right, so that they're both in the positive x direction. And so that's the field components I'm going to worry about. Now all I've got to do is add those little guys up. So let's see if we can do that. Gosh, I keep doing that. Okay, so now we're going to find the total electrical field, which is actually the total resulting x component of the electrical field, which is actually just the sum of what we just wrote down, E1x and E2x. Just got to add those up. Well, that's pretty easy because they're both the same. And so I'm just going to get 2 times kq over r squared times cosine theta. And then finally, I'm just going to rewrite this a little bit. It's why I wrote, why did he do that? Why did he make such a big deal out of cosine theta being adjacent over hypotenuse? This is why. I'm going to replace this cosine theta with a over r. Let's go ahead and do that. And if I do that, I'm going to write the answer in a particular way. I get the following equation. K times this factor in parentheses that depends on, if you look at it, depends on the charges and where they're located, divided by r cubed. That's the distance we are from the charges. And so that's our result. Look, that's a nice example of all what we did in today's class. We used the concept of the field, we used the field of point charges, the similarities and differences between the fields of positive and negative point charges, and we used superposition principle and vector addition to find the net field. So we solved a substantial problem here, and the result that comes out is very interesting. So one conclusion is that the electrical field of a dipole is, it doesn't go as 1 over the square of the distance from the dipole. It actually goes over 1 over the cube of the distance. That's the characteristic of dipoles like water molecules. Their fields fall off quicker, more quickly than inverse square law. They fall off as an inverse cube law. So it's very interesting. The field around a dipole, like a water molecule, is strong near it, but it quickly goes away. The other thing that's interesting is this piece in parentheses here. The strength of a dipole depends on the product of 2 things that describe the dipole. It doesn't just depend on the charge. It depends on the product of the charges at the 2 ends of the dipole and their separation. So you can make a dipole bigger if you increase the charges at the plus and minus ends, or if you increase the separation, or if you increased both. So if I got a water molecule, I grab a water molecule and I pull apart the oxygen and hydrogen ends, that's going to make a bigger dipole. I'm not changing the charges, but I'm changing the separations. And so that quantity, 2qa, is actually called the electric dipole moment. It characterizes the strength of the dipole. And so that's the other important point here, that it's proportional to the, not just the charge, but the dipole moment, 2qa. That's almost illegible, but here it is. Okay. I want to talk about how to, so we've done a lot of math. Heart rates are up. My heart rate's up because I've been using that document camera. Let's try and relax and just draw, sketch, like going back to kindergarten. We're going to draw some electrical fields, sketch some electrical fields. And we do that with field lines. So what I'm going to show you, firstly, is how we sketch the electrical field of a positive charge, a negative charge. Then we look at the electrical field of a dipole we've met, and another few important electrical charge configurations, what their fields look like. And we're going to learn how to draw electrical fields by drawing electrical field lines. It's a very helpful thing. It does sound kindergartenish that, adults, professional scientists are drawing electrical fields, but we do that all the time to better understand, comprehend electrical fields of charge distributions. Okay, so here's, as a building block, here's my sketch of the electrical field of a single positive charge. Here are what we call the field lines, these lines with arrows located on them. How do we read this sketch? Well, the density of the electrical field lines, how closely they're packed or loosely they're packed, indicates the strength of the electrical field. So if you see the field lines are closely packed together, that's a strong electrical field. If they see that they're loosely packed together, then that's a weak electrical field. So near the charge, that's a strong electrical field. Further out, this is a weaker electrical field. Second point, the direction of the field, E, is given at any point by the direction of the field lines at that point. So if I'm downstairs here, the field itself is downwards. That's the direction the field line points in because of the arrow here. If I'm upstairs here, the field is up because of this arrow here on the field line. Over here on the right, the field is to the right. The arrow is pointing towards the right. Over here on the left, the field is towards the left because the arrow in the field line is pointing towards the left. And so that's how you read the strength of the field and the direction of the field from the picture of field lines. Certain things that field lines don't do. Field lines always begin on positive charges. That's a very important rule. So if you're drawing a field line starting somewhere in space, there better be a positive charge there to create that field line or field lines. The other thing that field lines never do, field lines never cross one another. If you think, what would that mean if they cross? That starts to get into ambiguity, the world of ambiguity. Because then you don't, if they cross, at that point they cross, you don't know which direction the field is pointing. So those are two rules about field lines. If you want to picture a field vector based on the field lines, that's what I've done in this sketch here. In addition to the field lines, I've pictured little vectors, little arrow vectors at different locations. You can use the field lines as guides. So here, right, the field lines are more closely packed. I pictured a strong electrical field, a large electrical field vector. Here I pictured a much smaller electrical field vector because the field lines are more loosely packed. Here, I use the neighboring field lines to guide me in the direction. It's somewhere between this guy here and this guy here. It's closer to this guy. Again, here, I use the neighboring field lines to guide me in the direction of this field vector. The next two slides, exactly the same thing for a negative charge. So there's not much new on the next ones. We're just going to look at it. So I'm going to look at it more quickly for a negative charge. So here's the negative charge. Again, here's the negative charge. And the density, how closely or loosely packed the field lines are, tells you the strength of the field, and the direction of individual field lines tells you the direction of the field. So look, here, near the negative charge, the field lines are densely packed. And so this is a region of strong field. And here, far from the negative charge, this is the region where the field lines are loosely packed. And so this is a region out here, a weaker electrical field. If I'm downstairs here, below the negative charge, the field is up towards the charge. If I'm upstairs here, the field is downwards towards the negative charge because of this arrow. If I'm on the right, the field is towards the left. If I'm on the left, the field is towards the right, always pointing in the direction of the field lines. Mind you, those rules. So field lines never end also in empty space. They always end on negative charges, like field lines always began on positive charges. So think of that as the rule. Field lines originate from positive charges. Field lines terminate on negative charges. The other rule still applies, right? Field lines can't cross because field lines crossing is completely ambiguous. One final rule, one final statement is that you noticed on my pictures, this picture here and the one of the positive charge, the field lines kind of went outwards from the positive charge or came inwards towards the negative charge. The field lines can end when they go off the picture, right? So I'm not implying that these field lines terminated here. I'm just imagining that they head off into the room, vanish into the room. Likewise, on my picture of the positive charge, I didn't imagine that the field lines ended at some distance from the positive charge. I'm just only drawing the picture out that far. I'm imagining that they drift off into the room. And so often our pictures of field lines is of a field over a limited region, and we allow them to sort of vanish away on the outskirts of that little drawing, that little sketch. These are field vectors drawn from this field pattern. Again, this one's larger because the field lines are more densely packed. This one's smaller because the field lines are more loosely packed. And I'm using the direction of the field lines to guide me in the directions of these field vectors. Okay. This is the picture of the electrical field of an electrical dipole. So this is the picture of the electrical field of a water molecule. If you could see the electrical field of the water molecule, it looked just like this. So an electrical dipole, like a water molecule, as we said, has positive and negative ends separated by some distance. And I've arranged this dipole. The positive end's over here on the right-hand side. The negative end is over here on the left-hand side. And so this is a dipole. It would be characterized, the dipole's strength, the dipole moment would be characterized by the product of the sizes of the charges that are on the plus and minus ends times the separation of those charges between the plus and minus ends. So let's take a walk through this field. Now knowing, right? We now know how to read a electrical field sketch, an electrical field diagram. So let's point out a few interesting regions. Supposing I was close to the positive charge here. If you're real close to the positive charge and the negative charge is far away, basically you just see the field of the positive charge. There's barely influence of the negative charge. So the field lines just come radially outwards of the positive charge. And because you're close to that charge, the field is going to be strong. The lines are going to be closely packed. And so that's what you see in this region here. Look, the field lines are just coming radially outwards, and they're very tightly packed. It's similar around the negative charge. If you're nearby the negative charge and you're far from the positive charge, then you're basically just going to see the field of the negative charge. And the field of the negative charge is a field where the field lines just come radially inwards towards the negative charge and terminate on the negative charge. And it's going to be a strong field because you're close to that negative charge. And so that's what we see in this region here, close to the positive charge, in this region here, close to the negative charge. What about far from the dipole? Now you can't, on this diagram, right, I can't really walk that far from the dipole because I'm going to walk off the slide. But let's imagine we walk off the slide, upstairs or downstairs, or to the left and right. What's the field going to look like? It's going to fall off much quicker than the field of a single positive charge or a single negative charge. The reason is the field falls off more quickly, and you can see it on the diagram, is that field lines that are emerging from the positive charge kind of get captured by the negative charge. If you look on here, say we take this field line here. It starts emerging radially from the positive charge, but then it's starting to be captured by the negative charge and ends here. It doesn't get off the screen. Take another one down here, right, this one. It starts emerging radially from the positive charge, but then it gets pulled in towards the negative charge and gets captured, terminated on the negative charge. So if we had just the positive charge on the overhead, then all its field lines would escape the slide. If we had just a negative charge on the screen, all the field lines must come in from outside the screen to the negative charge. But with a dipole, a lot of the field lines are coming out of the positive charge but being captured by the negative charge. So less field lines get away, less field lines escape. And so that's why the field falls off much more rapidly than the inverse square law field of a positive charge or a negative charge. And we've learned it falls off as 1 over the cube of the distance. So here's a visual understanding of that 1 over r cubed, 1 over r to the power 3 dependence of the electrical field of a dipole. There's another interesting region we might look at here, this dotted line here. This is what we call the midplane of the dipole. So any point on that midplane is halfway between the positive charge and the negative charge, in the sense that the positive charge and the negative charge are equal distances away. In that case, that's the case we worked out quantitatively. In that case, the vertical components of the electrical fields due to the positive and negative charges vanish. They cancel each other out. So they add up and make 0. And only the horizontal component of the electrical field remains. So it points from left to right. And that's what you're seeing here. This is the field along this line that we calculated. We calculated that it was towards the right from the left, and we calculated its strength in terms of the dipole moment and the distance from the center of the dipole moment. Anyway, that's a dipole field. I think I'll skip that. One other field I wanted to show you, and then I'm going to show you demonstrations of these fields, is another very important field that we're going to meet during the semester. And it's the field of a circumstance, a situation in which you've got two metal plates. Imagine I've got 2 big metal plates. And I put positive charge, I've smeared it out on the left-hand plate, and negative charge, I've smeared it out on the right-hand plate. That's what I've done here. So that plate on the left has got positive charge spread evenly all over it. That one on the right has got negative charge spread all evenly over it. Now we know that the one on the right will be the source, the origin of field lines. The one on the left, the negative one, will be the termination, the end of the field lines. And in that arrangement where you've got 2 big sheets of positive and negative charge, in the region between the sheets, the field just sweeps uniformly from the left-hand sheet to the right-hand sheet. This is a very important electrical field because it's how you make a uniform in size, uniform in direction, electrical field. And so here you see, you look at these field lines, then they're equally spaced everywhere, which says they're packed as evenly, That's a uniform strength electrical field, and they're the same direction everywhere. And if they're the same direction everywhere, that means that the electrical field is the same direction everywhere. And so that's a very important situation. Here is the electrical field of a single sheet. Imagine this is a single sheet. The toothpicks are the field lines coming out of that sheet, if that was a positive charge, or going into that sheet, if that was a negative charge. So that's how to picture that. We'll meet that situation later on. Here's the field of a cylinder of charge, or a wire of charge. The field lines come radially out of that. If it was a positive sheet, a wire of charge, this would be field lines coming outwards. If it was a negative charge, this would be field lines coming inwards. Okay. I think I want to show you these demonstrations. I'm going to put the camera on, if I can. Where did the camera go? Okay. In here we don't need the camera. This is just, I'm recording it, so we'll want the camera for that. But we're going to look at this overhead here. So in here, I've got this sheet. It contains inside it, there's a little rectangular vessel that contains some oil, like I think canola oil from Kroger's. And it contains these little green microscopic particles. I don't know what they are. But if I put this in an electrical field, the little particles in the oil orientate themselves to the electrical field. What they do is they cluster together where the field is strong, so you can see regions of strong field, and they also turn themselves to point in the direction of the field. And so we can map an electrical field with this little sheet here. So I'm going to shake it up. You shake it up, and then I'm going to put it in this arrangement. And because I've shaken it up, these little particles are all over the place. But now I'm going to add a device that allows me to make an electrical dipole field. So I'm going to make one end of this device here say positive, and the other end negative. And so we're going to see the field of an electrical dipole that we've been talking about. I'm going to charge it up with this. This is a handheld Van de Graaff generator that we met in class. And so you're seeing gradually, right, that, I don't know where to put this, that pattern of field lines emerge. You've got field lines that are heading into or heading out of one of these two charges. One is plus and one is minus. And you see look over here, you see the pattern of the field lines looping through space from one of the charges to the positive one to the other one, the negative one. And so that's a way of picturing, detecting this electrical field that I just created. I find that I could watch this for a long time, actually. It's very relaxing. You see, after time, you see little bits moving around. It really does feel good. But I want to show you the second case. I know that in psychology, there's all types of therapy. I'm getting off topic a little bit, but I've got this idea of electrical field therapy in which we just sit back and watch these electrical field patterns, and we all relax with it. So I'm going to show you another one. First thing I've got to do is shake up this guy again. So, because I want that field to go away. So I got rid of that field. And now I'm going to put in a second device. This is going to get the field of two parallel plates. So it's going to have one positively charged plate and one negatively charged plate, and we're going to see this field. Dog's growling at me. If I brought my dogs in, they wouldn't be sitting here like this dog. They would be flying around this room like crazy. It would be quite difficult. Okay, so here's the electrical field of two charged plates. This is positively charged, negatively charged, say, and this is the uniform electrical field between the plates. You can see the material, the little particles, kind of lining up in field lines. At the ends of the plates, you get what's called the fringe field. There you see the field lines kind of loop around a bit. You get what's called a fringe field. And again, if you keep watching this, you see these little particles, whatever they are, I'd love to know, just gliding around, telling you what that field looks like.